Welcome everyone. This is Nassim Magdi for your YouTube channel, Nassim Tron. Today we will speak about the James Webb Space Telescope with our very special guest, Dr. Don Lincoln. And actually, I'm very happy to host him in the YouTube channel. I should mention that one of my like I would say, I get inspired by his YouTube videos to start mine. So it's a great pleasure to have you in the show. And actually, Dr. Lincoln, he's a senior scientist at Fermi Lab, America's flagship particle physics laboratory. He has over 30 years of experience exploring the most fundamental laws of nature. He has participated in some of the key discoveries of the last few decades, including the discovery of the top quark and the Higgs boson. He's an active writer about scientific topics aimed at non-scientist audience. He has written many books, magazines, articles, and blog posts. He has contributed to CNN, Nova, and Life Science. In addition, he used the power of the internet to bring engaged video to broad audience. Thank you so much for being here and welcome.
Oh, I'm really glad to be here and I appreciate the invitation.
I would like to start the discussion about James Webb with one of the misunderstanding points in the Middle East about telescopes. So one of the statements I heard that is a time machine that can tell us about not the past of the universe, but the past of everything. So one of the statements that I didn't like at all is if we are looking using the telescope to look back to Earth, we will see the dinosaurs walking on the surface of Earth using the data getting out of the telescope. I know that this was not it's not what's happening, but I would like to hear from you about that. Like, how can one explain the relationship between the light that we collect using the telescopes and the history of our universe? I think that's the main target here.
Well, there's two important things that you need to know to answer that question. One is that light travels at a fixed speed. It travels at 300,000 kilometers per second. So it's fast enough to go around the Earth about 7 times in a single second. It's very fast, but it's not infinite in speed. And the other thing is the universe is very large. The sun is about 150 million kilometers from Earth. And it takes 8 minutes for light from the sun to get to the Earth. So when you look up at the sky and you see the sun, on some wonderful summer morning, you are actually not seeing the sun as it is. You are seeing the sun as it was 8 minutes before. So in some sense, that's how you can call it a time machine, because the things you see, you're not seeing them as they exist now, but as they were in the past. And if you go to other astronomical bodies, the nearest star is Proxima Centauri. It's 4.3 light years away, which means that the light that we're seeing it is 4.3 years old. We're not seeing it as it was now. If it blew up today, and it won't, but if it did, we would not know about it for over 4 years. So looking deeper and deeper, the next galaxy over, the next, I should say, large galaxy, Andromeda, is about 2 million light years away. So we are seeing light that was emitted from Andromeda before humanity evolved, before modern humans even existed. We're seeing the light as it was emitted now. So by looking at more and more distant objects, we can look farther and farther back in the universe. And that means as we get to very long distances, if we look at galaxies that are 10 million light years away, or 100 million light years away, or 1 billion light years away, we can actually see galaxies that existed before the Earth even formed. And so by looking at farther and farther away, we are actually looking farther and farther back in time. We're not looking back in time where we are now, of course, that's not what we're doing, but we are looking to see what galaxies looked like, say, 100 million years ago, 1 billion years ago, 10 billion years ago, and we can see how they've changed over time. It allows us literally to see the evolution of the universe. Now about dinosaurs and so forth, obviously we cannot turn the James Webb Telescope and look at the Earth to see dinosaurs. However, if we had a hypothetical, very powerful telescope, when we moved it millions or tens of millions of light years away, we would be able to see light emitted from the sun that the dinosaurs saw, that only is now getting that far away. Obviously, the telescope's not powerful enough to see dinosaurs. That's not possible. But it would be possible if somehow we had a telescope that was, say, 65 million light years away from Earth. The day that the dinosaurs died, when the meteor hit Mexico, we would see that light, even though it happened so far in the past. So I think it's fair to call things like these big telescopes, the Hubble Space Telescope, the James Webb Telescope, they are sort of time machines. They do allow us to see not our history, but the history of the universe.
That's a point I would like to make, actually. It's we see the light that will be at that time, not the actual picture from inside the Earth at that time. And that's the difference I would like to make, because it was a misunderstanding point that I think people got it wrong. So usually we have this kind of weekly meeting with audience from Middle East to ask physics question, and one of the main questions, okay, if we had that telescope, we pointed through the Earth, can we take like a picture of the activities inside Earth, like the life of the dinosaurs, daily life of the dinosaurs on Earth? And that's very nice to explain that we're speaking about the light that might be reflected or emitted by the object itself. That brings me to my second question related to that. The James Webb Telescope is not our first telescope. I think we had like different telescopes before. I can just relate to two right now: the Hubble telescope, which will be looking into the visible light, and of course after that we had the Spitzer, which will be in the infrared. And my question is like, okay, so why we need a new telescope, and especially why we need it to be in the infrared wavelength?
Right, so there's a lot of answers to those questions there. The Hubble Space Telescope was launched 30 years ago, and it's been a magnificent facility. It's allowed us to look deep into the history of the universe, and we are able to look very far back. In fact, the most distant object that we have ever imaged is, let me think, it is 13.4 billion years old. It is the most distant galaxy, and a combination of the Hubble Space Telescope and the Spitzer Telescope has allowed us to take pictures of them. So that's already pretty amazing. The universe is 13.8 billion years old, and we can look at things that are 13.4 billion years old. So that only leaves 400 million years of the early universe that we have not been able to see. So as you said, the Hubble Space Telescope is magnificent in that it takes pictures of visible light. It takes pictures of the things that we could see with our eyes. The Spitzer Space Telescope does not. It looks at infrared. Infrared is not something you can see with your eyes. You can, however, feel infrared with your hands. You feel heat. Now, the heat that we get, of course, from distant stars, you can't feel because it's too little. But that's what infrared is. It's essentially heat. The Spitzer Space Telescope has allowed us to see basically hot things distant hot things. Now, this is pretty amazing. It allows us to actually look at some very large planets that are at stars that are, of course, far away, but not many galaxies away, but within our solar system. We've actually even been able to use the Spitzer Space Telescope to image the weather on planets around other stars. So that blows my mind. So you ask yourself, why do we need a more powerful telescope? Well, at some level, it's because technology has evolved. The Spitzer Telescope was more recent than the Hubble, but it was made with a technology that was not as good as what we have now. The James Webb Space Telescope will be 1,000 times more powerful than the Spitzer Space Telescope is. It is much larger than the Hubble Space Telescope. The Hubble Space Telescope has a diameter of 2.4 meters. The James Webb Space Telescope has a diameter of 6.5 meters. So it collects a lot more light. It collects 7 times as much light. And so essentially, in the same way that you might ask, where Galileo made the first little telescope that he could look at with his eyes, and he was able to see the moons of Jupiter, but he was not able to image with any detail distant galaxies, you needed better and better telescopes. And so over the course of the last hundreds of years, these bigger telescopes have allowed us to see more distant things with better precision. And that's the first reason, is we are able to make things to be able to see astronomical bodies in more detail. But the question you ask, and this is a very fascinating one, why does the James Webb Space Telescope need to be infrared? And the answer is, at some level, it doesn't. We could make a telescope that could be in any wavelength, but we want to answer a specific question, or actually a couple of specific questions with the James Webb Telescope. And for that, infrared is necessary. I told you that we were able to see the one galaxy that is 13, or the light took 13.4 billion years to get to Earth. That means that there's 400 million years from the beginning of the universe to then that we've not been able to see. Now, it's kind of tricky what happened, because the universe was once smaller and hotter and the entire universe glowed. And it glowed for a long time, about 400,000 years, 380,000 years, at which point the universe cooled enough that it was dark. And then from that time, literally, it was called the Dark Ages. You can see nothing because there were no stars. There was just gas, invisible gas, which slowly, under the strength of gravity, pulled together and slowly became denser and denser until the first stars actually started to burn. We think the first stars started to burn between 100 and 200 million years after the Big Bang. So the James Webb Space Telescope is being built, or was built, I should say, and is now beginning operations, to attempt to look at the very first stars that existed in the universe. So why do they have to be infrared? Well, that's actually tricky, and it's kind of interesting. The first stars in the universe were very large. They were at least 100 times larger than our sun. They were very hot. They burned very bright. They burned very blue. They were a very intense light. And that's not infrared. That is very, what we call, high frequency wavelength light. But even though those stars were so very bright and so very blue, the universe is expanding. And so this is very hard to get your head around. So what happens if an object is moving away from you? If an object is moving away from you, it appears to have a different color than it really does. Now that is hard to understand, but you have a feeling from this that you can get from hearing. Light is made of waves, sound is made of waves. So if you've ever been at a racetrack, automobile racetrack, or if you've ever been near a train crossing where you hear a train whistle as the train is coming towards you and as the train is moving away, you hear there's a change in frequency. It goes, and so that change in sound is from short wavelength to long wavelength. And that's just the nature of a thing called the Doppler shift. And so if something's moving away from you, it has a lower pitch if it's sound. But if it's light, what it has is it looks redder. So if an object is a certain color and it's moving away from you, it appears more red than it did before. And the faster away it moves, the redder and redder it is. Eventually, it gets to be moving so fast away from you that it's not red, it's infrared. So it is no longer visible. It's not something you can see. So these distant stars, even though they were very bright, white, blue, super hot stars when they were born and when they burned, and that light they emitted was very blue and very hot. By the time it came here, the universe has expanded. These objects are moving away from us very fast. And the light that we see now is not bright white. It's not blue, it's infrared. And so only an infrared telescope will allow us to be able to look at the very most distant objects. So if you want to see these distant objects, the only way to see them is with a powerful infrared telescope. And that's why the James Webb was designed the way it was.
That's great. Also one of the I should say right now, I actually had a recent video on the Doppler effect. I need to explain some information about the Big Bang, and I know I will go to the redshift. So I start first with explaining the Doppler effect, but I will put that in the video description. But also one information I read about the infrared, why James Webb Telescope should be in infrared. And he was speaking about the dust in the outer space. And he even was speaking about that in one of the, I wouldn't say problems, but one of the, when we use Hubble, one of the deficiency of that is that we had the dust in the outer space, and that caused a reflection or a deflection to the visible light. But of course, when we go to the infrared, the wavelength is a little longer than that, so it will not be as reflected as the visible light. So that may be also an addition point we can add to the nice points you put already.
Sure. I mean, people can think of the dust as like a fog, but think of it as a fog that allows some colors through and not others. So suppose you have a rainbow that's very far away and there's a fog between. If that fog scatters away the blue light but allows red light to come through or so, then the object you will see, even though it was the rainbow of colors, only the red light will get to you. And that's essentially what you're talking about. The dust will scatter away the light you can see, but it does not scatter away this infrared light, or not as much. And so it allows us to be able to see in that wavelength, which is kind of cool that, it's by selecting the light that you use, you're able to see something that you couldn't otherwise see.
Actually, one of the questions that's sometimes comes to my mind when I read about the James Webb Telescope is the timeline. I think the project was initially planned at like 1999, and then was originally planned to be started and operated in 2007, but then it get pushed back by redesigning and by other issues until here we have in I think December 2021. So yeah, it's operating right now. It's out in the outer space. But what do you think are the main challenges that the group designed and built the telescope faced that took them all that long time?
There's a lot of things. I mean, this is a telescope involving technologies that hasn't been used before. The Spitzer Space Telescope was able to use to look at infrared light, and furthermore, and we'll talk about this a little later, the space telescope needed to be, not the whole telescope, but the electronic devices that converted the light into electricity needed to be very, very cold. And that was not something that had been done in space before. In addition, the Hubble Space Telescope is only about, I guess it's about 500 kilometers up. It's orbiting the Earth very close. So it is possible to send the space shuttle or some other spaceship up to go and have astronauts fix it. The Hubble Space Telescope is going to be much farther away. It's approximately 1,500 kilometers, not 1,000, 1,500,000 kilometers away. And it's simply impossible to service. So it has to work. That's number one. In addition, the Hubble Space Telescope is actually huge. It is about the size of a tennis court. So you've seen what people play tennis on, and it has to be all folded up inside a rocket that is only, I don't remember the diameter of the rocket, but it's maybe 8 or 10 meters across. So this thing has to all fold up, and it has to unfold without any help at all. And in addition, it was expensive. And there, when it is expensive, there's always questions about costs and cost overruns and who will pay for it. And the scientists had to motivate politicians to provide the resources that was needed to build this. And so you had funding issues, you had to make sure that there was support in the scientific community, and then you had these very, very difficult technical problems of causing something to fold up and unfold reliably without any intervention by humanity. You can't go out there with a wrench and turn a wrench and make something happen. It just has to work. And so given that it was expensive, there could be no mistakes. The engineers, technicians, and the scientists had to be absolutely certain that this thing would work. And so far, it has. That's the rationale. That's why it took so long, because it just had to work.
I really agree. Every time I watch the videos, how they design it year after year, how they test every single detail, every screw had to be in the proper place. Otherwise, yeah, we could waste all that money. So they did a great job. You start by mentioning the cooling part or the cryo part for the telescope, and actually also it blows my mind when we speak about here that we try to cool down the telescope to about like 7 degrees Kelvin, about minus 262 Celsius or minus 474 Fahrenheit. I think that's very, very cold. Why we need to go that cold for the telescope that's already in the outer space?
Well, outer space isn't always cold. Outer space can be quite hot. The sun beats right on you. So you have to have an amazing sun heat shield in order to keep it cold. But why does it have to be cold? Remember, what we are doing, or what the astronomers, the NASA and European Space Agency astronomers are doing, is trying to look at infrared light. And infrared light is heat. Now, you want to look at things that are billions of light years away, which means they're very, very, very faint. The amount of light that comes to the telescope is invisible to the human eye. You couldn't see it if you wanted to. So because it has to be magnified so very much, and the amount of signal is very tiny, and the signal is, after all, heat, if the electronics are hot, then what will happen is that heat of the electronics will swamp the heat that you get from the more distant galaxies that you want to look at. In fact, it would be like trying to listen to someone whisper 1,000 kilometers away while you're at a rock concert, because the noise at the concert is too loud. You would never hear the more distant thing. Similarly, if you did not cool down the electronics so that they're essentially silent, if the rock concert were silent, then maybe, just maybe, you'll be able to see that very distant thing. So that's the reason. The equipment has to be cold or it won't work. It's just the simple fact that if it has to be cold.
That's great. It's like, yeah, you try to minimize the noise in your signal. If
Yes.
your noise exceed your signal, so you're basically, I will quote my my advisor over here and say, like, you're measuring noise.
Exactly.
One of the points that we try to avoid all the time. And actually, since you will speak about the like try to get cool enough and more stable, usually people ask why we call it an L2 telescope, and I think that will be mostly related to temperature and setability. So why we call it an L2, and what's an L2 telescope mean?
Well, L2, back in the, I guess, 1700s, a mathematician and scientist by the name of Lagrange tried to understand how the gravity of the solar system worked. And the Earth orbits the sun. But if you then take the Earth and the sun together, now you have two bodies, and they both exert gravity. So he came up with 5 places around the sun where the gravity due to the Earth and the gravity due to the sun balanced each other out. So, and these are called L1, 2, 3, 4, and 5. L2 is the point that is about 1.5 million kilometers farther away from the sun than the Earth is. And the Earth, now this is kind of neat. So the Earth feels the strength of gravity from the sun, and it goes around the sun. But if you go 1.5 million kilometers farther away, then an object sitting there feels not only the gravity due to the sun, but also the gravity due to the Earth. And because of that object, because it has a little extra gravity, more than just the sun, that thing will orbit along with the Earth. And that's called the L2 point. So there are other of the Lagrange points, but the L2 point has a couple of wonderful features. One, it orbits with the Earth, so it's always the same distance away from us pretty much. Two, it's farther away from the sun, and that means that the Earth is actually trying to block some of the heat from the sun. And remember, the James Webb Space Telescope needs to see heat. So if you're able to block the sun, which is of course the brightest thing in the sky, it's very important to do that.
You minimize one of the main sources, yeah.
Exactly. And you still need a heat shield because the Earth itself is ridiculously hot compared to what the types of things the James Webb Space Telescope is meant to see. So L2 is just a certain point in space, and that is the point in space where the combined gravity of the Earth and the sun force it so that that object will orbit with the Earth, and it will be protected from the Earth, and it will allow us to look into space. So it was a clever choice. The downside is it's very far away, and so it's not possible to fix anything that breaks. So that was the downside. They had to balance those things, and it gets back to why it took so long to build.
But now, since the telescope is out there, I think hopefully soon will be ready to operate and work and collect data. I would like to end with what are the expectations from the James Webb Telescope? I think you mentioned several of them along the way, but if we would like to summarize what we expect to see or what we expect to capture from the James Webb Telescope.
Well, I'll tell you that, but what I'll tell you, I hope we'll find something we didn't expect, because that's the most fascinating place.
That will be more interesting.
Well, no, absolutely. Seeing what we expect to see will be fascinating.
Yeah.
But I always want to be surprised. However, there are two primary things that the James Webb Space Telescope is built to see. One is to see these very distant galaxies where the first stars came to life. So literally the first stars ever made in the universe, we'll be seeing some of them, assuming everything works. That's the first thing. The other thing, and this is incredibly fascinating, is humanity has always looked up in the sky and wondered, are we alone? And we really had no idea about that. We didn't know if other stars had planets. We assumed they did, but we didn't know that. Now, in the past 20 years, we've actually been able to see evidence that other stars have planets around them, but it was not possible to actually look at the planets themselves. However, with the James Webb Space Telescope, we will be able to look at nearby stars, but still very far away, and actually image the planets. We'll be able to take pictures of planets. Now, you won't see all planets. You would not see an Earth-like planet. The only planets we'll see are the ones that are very hot. So we will see ones that are very close to the sun, or not sun, close to the star, and they're heated up by the heat. Or we will see what they call protoplanetary disks, which are cases where the gas and the dust around that star are starting to coalesce and make planets. But the thing that I think is the most fascinating is that the James Webb Space Telescope will be able to look at a few classes of planets and actually figure out whether it has an atmosphere, an exoplanet, a planet around another star, be able to see whether it has an atmosphere and even work out some of the chemistry of the atmosphere. We might even see, if there's atmospheres like our own. That's a bit of a stretch. It's going to be hard to do, but that is one of the expectations, that after some observing, we'll be able to do that. The James Webb Space Telescope was designed to operate for 5 years, but the launch was very successful and it used very economically the fuel. And so now the hope is, if nothing breaks, that it will operate for 10 years. And so during that time, the telescope operators will figure out ways to use it better and better. They will develop their techniques. They will learn how the telescope works. And I would not be shocked if we are able to actually image weather on distant planets.
Wow. That will be really, really interesting. I think that's one of the main questions that humanity had been asking like all along. Are we are alone in this universe, or some
Would be cool.
nearby civilization? Who knows? I'm really happy Don. You answer all of my questions. I think I'm very, very thankful for you for the time and the effort.
I would just well, first I'd like to thank you for inviting me. It's always a pleasure. And I enjoy talking to the public about science. It's my passion, and I'm glad that you give me the opportunity to do so to your audience. And what I would like to say to your audience is science is wonderful. Science has made our life much better. No longer do we live in caves, scared at the lightning storm as the lightning god fights the demons that surround us. We now have become masters of the universe. We understand the universe in which we live. There's a lot more to learn, and facilities like the James Webb Space Telescope are how scientists have made the progress that they have. And so I'm fascinated by what we'll be seeing over the course of the next 10 years of operation, and I hope you will be too. Furthermore, I hope you'll be interested in all sorts of scientists. I'm sure Nassim will tell you about many fascinating technologies, fascinating facilities, fascinating questions, and it's science. So I'm pleased to be part of it, and I'm pleased that young people like Nassim are getting involved. And I hope that you, the viewer, will find it as fascinating as we do.
Thank you so much. I really find it, I think, inspired by you. I started all of that, and I hope to bring more knowledge to the public audience and non-scientific communities. By the end, I would like to thank everybody that watching this video, and thank you all for being with us. Thank you.
Thanks again. Thank you very much.